and I did my hackathon project on help defense and how a team could use that to minimize the efficiency of an opponent. Let's look at this example. You can see the Warriors represented by the blue polygon here, and the Rockets represented by the red polygon. You can see that Andre Iguodala is helping off of Ryan Anderson on that left side of the court. And I noticed that the difference between these two areas was actually large. The blue is obviously much smaller than the red in this case. And so I thought, well, maybe that's a representation of how much help defense is being played. Let's look at another scenario where Clint Capella has the ball up top. Nobody is worrying about helping off of their defender, off of their guy to help on Clint Capella, and they're stuck on Houston's shooters. And you can tell the areas are, while not completely the same, they're more similar. And so the difference in those areas is lower, representing probably less help defense being played. So I'm here to talk data to you. How did I get to this point, and how do I weaponize this difference in the area between offense and defense so that people could be effective in creating good help defenses? So first of all, the help metric, I calculated the convex hole area of the offense and defense, took the difference between the two, which I'm going to call my help metric. I found this by some work with Stephen Shea and Chris Baker, and I branded it as the help metric because of what I saw in those scenarios. And then I used some of the play-by-play data from Basketball Reference as well as the data that we were given to identify half-court possessions. Help defense is a different beast in fast break scenarios, so I wanted to limit it to just half-court scenarios. And then to measure the efficiency of the opposing offense, I built an expected points model, which can be built using those probabilities that you can see there. And I built it on ball handler specific plays. So in this specific scenario, I'll show you I scouted James Harden, but this could be built for any player in the league on a scouting basis. To model those probabilities, I used the dependent variables of the spatial location of the ball handler in X and Y, the distance the ball handler was from the hoop, and this help metric that I've created. And those probability models were built using some random forests. They had really good AUCs, so I was pretty pleased in a hackathon amount of time to get something like this. So how do I then use that to determine the optimal amount of help a defense should have? You can see in these three scenarios where we have paint, the ball handlers in the paint, the ball handlers in mid-range, and the ball handlers at the three-point line. It's pretty messy, but around a 300 difference between the two ended up kind of being the sweet spot of minimizing. Remember, we're trying to minimize that expected points value on the y-axis. And so convex hole difference of 300 is what I'm going to use to define the optimal help defense for the next scenarios I'm going to show you. So like I said, I built this to scout James Harden. So the Houston's expected points per possession when James Harden has the ball is mapped by James Harden location on this heat map, and then the expected points on a blue to a higher version of expected points in red. You're not going to stop James Harden from scoring. If you give me a metric and this plot is blue, I'm going to tell you you're either a wizard that figured something out or your model is obviously messed up. But how does this compare to maybe some other help defense scenarios? Because remember, in this specific case, we've optimized help defense at that 300 area. If we overhelp and sag off of some of Houston's other shooters, you can see James Harden starts finding people in the three-point, and Houston scores a lot of three-pointers, essentially more expected points on average than the optimal help area. Conversely, if the teams were to not help at all and suck up onto their respective guys and the shooters, James Harden starts to hit you with his patented step-back J and ISO, getting a lot of threes, is also able to get to the lane on you because there's no one inside to help off of and help guard in the lane. So I found that very interesting, and it seemed like this optimal help was a good sweet spot to minimize the effectiveness of the offense in this scenario. So what, cool, I built this cool probability model and this help metric. I'm pretty sure that Steph Curry, when he's guarding James Harden, isn't going to calculate the convex hole area as he's playing to optimize the amount of help defense he's going to play, right? That's not going to happen. So I think this could be effective in scouting a player. You have an opposing player coming in. You can run different simulations and scenarios to tweak your help defense and help optimize and minimize your opponent's ability to score points. It could also be used for self-evaluation, figuring out how effective your help defense was during specific games, which I think is really cool. Just like any advanced analytic, though, it's just another piece to the puzzle. If this can just be given as another weapon that coaches can use, my hope is that it could be used in ways that could help teams in defense where there's not as many metrics today. But I appreciate you guys coming, and it was really fun to work on this. Thank you very much. I'm used to the 90 seconds. Yeah.
I'm curious about how you defined, say, for instance, James Harden having a possession with the ball. Is it anytime James Harden touches the ball through the first shot? Is it through the end of a possession? What exactly is that metric, and how did you measure it?
That's a great question. I had a slide on it, but realized I only had 5 minutes. I defined it by the offensive player, so James Harden, that was closest to the ball on an offensive possession. And I found the offensive possessions by attaching the basketball reference scrape to the play-by-play data that we were given. Mike's coming back here. Yeah.
Yeah, so how do you can have the same help metric, but you can have a different configuration.
Yep.
How would you look at that to see, like, maybe if one player is moved over this way, it creates the same number, but a different spatial configuration?
Yeah, for sure. I think that's great. I think that goes to where you want to implement this statistic, where you'd want to run simulations, where you have say you're scouting James Harden, you have the offensive sets that Houston usually runs, and then you could configure your defense in what you think is the optimal help scenario, and then maybe tweak it here and there to see how it affected that expected points. Does that make sense? Yeah.
Great presentation.
Oh, thank you.
You probably said it on the expected value. What was the probability distribution, or the probability distribution of the variable you use? And secondly, all of your spaces were convex sets. Did you do anything with concave sets?
Great question. So I only use the convex sets to get the area between everything. And then in terms of the distribution of the expected points, I use a polycotomous tree and then did binary regression on each of those and then backed into the probabilities. You could do it in a multinomial case. It was just the fastest way for me to run at it during the hackathon.
Hey, my question was, were you able to define help? I know you said, I saw it was over help. I also saw in the beginning you kind of showed how they helped when they were on Clint Capella. But did you ever define, if there was someone that was helping halfway or helping 3/4, or 1 man away, that sort of thing?
Yeah, that's definitely a hard thing to get at, and I was hoping that the optimal area could define like when you're helping in the right way. And so essentially for the no help scenarios, I used the areas that were the difference wasn't very high, as explained in that second scenario. And for underhelp, when the areas are drastically different, people are helping a lot. So I kind of use that as the range between no help and overhelp, and then wanted to find the optimal distance. But it's hard to tell, and I think this is where it could be used in more of a scouting scenario where a coach could actually simulate where they think should be optimal, and then maybe make small tweaks based on this. Thank you.
All right, our next finalist from University of Bridgeport is Philip Mayhem.
Good morning, my name is Philip Mayhem, and today I'm going to tell you the secret of how to beat the Rockets. Hope Daryl's not here. No, good, we're all set. So gravity, you may have heard some things about gravity. You may think like Kyle Korver has a lot of gravity, right? Because people are always defending him. Kyle Korver has no gravity. He just has a defender in his face for 48 minutes. The other 4 players constantly play by themselves 4-on-4. That's not gravity. Real gravity, to understand real gravity, we have to look at things from a different angle. Is this the video not working? Oh, there we go. To look at things from another angle. So by the way, here we have 2D. We need to shift down to think of things in 3-dimensional space. We look at vector angles from the rim. Look at Harden here with going through with the gravity.
Oh, he just sucked the gravity right out of the building!
So watch Curry with the on-ball. When you see the vector angles, I'll explain in a second what's happening. He's got a lot of gravity when he's on the ball, naturally. When he's off the ball, see, you can't see him, but when he's off the ball, he still has gravity, but a little bit less, and that's going to be the key to figuring out how to beat the Rockets and how they can win. We're going to look at half-court plays only because that's all that really matters. For the purposes of gravity, transition doesn't matter. We're going to look at average defensive vector angle. What is the average defensive vector angle? Say I'm on offense. There's the hoop, so I'm shooting over there. You guys are on defense here. Think of the vector from the hoop to me and the vector from the hoop to you. That angle, the cosine, that angle is the vector angle. And we'll do that for all 5 defenders to me. So that average defensive vector angle is smaller when everybody is hedging from their man towards me. Does that make sense? So that's gravity. When the vector angle is small, the gravity is high. Now, I found a problem with this last night. I thought this was great, but it turns out there's a problem. If you look at the average defensive vector angle across all players on the court, this is off ball and this is on ball, you can see the pattern is there are some minute differences. There are obviously some differences across the space. And it makes sense when you think about it. If you're on the wing, there's a guy who's 180 degrees from you, so that'll change the average defensive vector angle, right? Does that make sense? So that's unfortunate. So we have to take that away. We have to look at the net of conditional effects. Do you know what serendipity is? Serendipity is when you have a stat called ADVA that nobody ever will remember, and then you need to add that it's net of conditional effects. That's serendipity. So let's look at who has the most on-ball gravity. This will be a bit surprising. So 3 of the top 4 are Warriors, McCaw, Thompson, and Curry, and Ariza's up there too. But look at the bottom. Harden and Paul seem to not have as much net gravity. This is surprising. There's 2 possible reasons for this. It could be that, I made a mistake, everything's wrong, everything's broken. That's possible. It could also be that people are not defending, the league as a whole is not defending Harden and Paul the way they have learned to defend the Warriors. And the reason I think that's suggestive that that's the case is because McCaw is up there too, right? It seems almost as if the league has decided whoever on the Warriors has the ball, hedge towards them. Hedge towards them, that's it, that's all they do. Off ball, who has the most gravity? Curry and Thompson, that makes sense. Now notice Harden and Paul, they're not at the bottom, but they're somewhere in the middle, and that difference will be huge. The net difference between the on ball and the off ball gravity, who has the most? Harden and Paul. The biggest difference between on ball and off ball. Now, what does that tell us? What is the secret of the Rockets' success? How can they win? They win not by having them be on ball or having them be off ball, but having them switch from on ball to off ball, because then they can play the defense like a yo-yo. Right? Harden has the ball, he passes it away, everyone sags. They pass the ball back to him, everyone collapses, right? Or vice versa. Does that make sense? So if passing in and out plays them like an accordion, plays the defense like an accordion, right? Without this gravity. So what can you do? Let's test this hypothesis. Let's see. Look at all the possessions where Harden or Paul had the ball for the entire period, 100% of the time, or 0% of the time. I predict that those should be the lowest productivity possessions. They should have very low productivity. It's only in the middle that they should have a lot of productivity, and boom, that's exactly what we see. At 0 and 1, they make between 0 and 1 point. It's when Harden has the ball about 40 or 50% of the time that they score 2 points per possession. Same thing with Chris Paul. Now, if we look back, one of the people in the middle who had very little difference between net gravity on and off court was Klay Thompson. So we would expect this to not hold for Klay Thompson, and what do we see? Lo and behold, it's true. It's not the case that we have that same sort of semicircular arc for Klay Thompson. We can also look at Harden's and Paul's overall net gravity, the advanced stats, net of the conditional effects across the court. This is Harden, this is Paul. And that's what we see. So that's gravity from another angle. Thank you very much. Questions? All right. Thank you.
And our last finalist in the open division, Dan Finkel from National Instruments.
Thank you very much. So I wanted to really embrace the storytelling aspect of this, and when I was asked or posed the problem of what story do you want to tell about the Houston Rockets and Golden State Warriors, I naturally gravitated towards the MVPs, so focusing on James Harden and Steph Curry. I wanted to focus down on 3 questions. How do they play the game of basketball? How are they defended by their opponents? And lastly, how do they impact their teams? So next chart, please. Oh, I got it. Let's see. Excellent. Okay, so you're already familiar with the contest itself. The one thing I did want to make sure I made a point here is to thank the organizers and the sponsors and the judges as well. This was a really cool thing. I've been to plenty of conferences where there aren't hackathons. I think more conferences should have hackathons. I think all of you should enter them and participate in them. It's a great way. It's been a blast. I had a great time with it. So I imagine, like most of the contestants and people that engaged with this, I took a 3-step approach to the problem where first thing I had to do was go back and read and understand the data. The next thing I did was I extracted and tried to understand features that were contained in the optical data. And then lastly, I tried to create a story around that, the features that I found in the data, and you'll see that coming up here. This data is awesome. As someone who doesn't work in the sports analytics industry, this is amazing data. You can learn a lot about the game just by looking at this data. Here's a couple of here's a couple of the things that I was able to back out and derive. I think some of the other competitors found this as well. It's really easy to find, figure out who has the ball, what team has the ball, figure out if they're in a half-court offense or if it's a transition. You can identify shots and baskets. You can also pair offenders to defenders. And you can make movies from this. I don't know, are you able to play this? What's that? Oh, nope. Awesome, thank you. So you can play out the data, and it's pretty neat, and you can kind of see, you can watch and see how these different extractions of the data perform. You can see how the defensive pairing comes out. We'll talk a little bit about those black circles in a chart here as well, and you can see it play out. So it's pretty neat, pretty amazing data. In terms of features, I focused on 4 different areas. Not so much a gravity derivation, but I looked a little more carefully at defensive positioning. So relative to an offender, where does the defender place themselves in terms of cushioning themselves against that defender, as well as how much do they shift over towards the ball? What's that angle of separation between themselves and the vector of the offensive player and the net? In terms of real estate, I used this approach called Voronoi partitioning. It's a very fancy way of saying something that's very intuitive, which is you identify each square on the court and you label it to a player based on its proximity to each of the given players. So a square, if this square in here belongs to me, something that's closer to someone over there, that belongs to them as well. And you can create those boundaries that are shown in black there as well and come up with a real estate from that. I also looked at court coverage as well, that paint that I showed you in the last chart of during a half-court set, how much of the court does the ball end up covering and containing? And then lastly, I looked at some traditional things like distance to the rim as well. Okay, so jumping into the story, there were 3 elements that I kind of jumped on and focused on. The first was court positioning from this data. It's very easy and straightforward to understand where these 2 players find themselves on the court. It's a really interesting contrast. On the left, you can see James Harden, especially on the offensive side, tends to hang out around the 3-point line, if any, and it's very nicely centered in most cases, at least for the 3 games I showed here. On the right, Steph Curry. Steph Curry, the heat map suggests he never stops moving. He's just whirling around the court the entire game. So it's an interesting way to contrast how the 2 approach the game and play it. And this visualization, I think, helps understand that. Next thing I looked at was defensive positioning. So how do these 2, how are these 2 defended by their opponents? And there's 4 metrics shown up here, and I'll step through them really quickly. First thing I looked at was how many of the plays in the half-court offense are they double teamed? Steph Curry faces a lot more double teams than James Harden, and that bore out in the data. The next thing was I looked at that real estate that I showed you on the last chart. How much real estate are they given in that black or Voronoi region? And you can see, just to reinforce that Steph Curry has a much tighter space when he has the ball. The third thing I looked at was defensive cushion. So how much cushion is the defender giving each of these 2 players? These strip heat maps kind of indicate where, in terms of footage, you see most of it. And again, you can see that they're defended in much different ways. James Harden gets a couple feet more cushion than Steph Curry does, and I think that fits kind of your intuitive understanding of how they play the game. And then the last thing was how much of their defenders cheating over to the ball. And it's subtle in this data, but what the data suggests is that Steph Curry's defender, while giving him less cushion, is also starting to cheat away from that vector of Steph to the basket as well, and thinking about where the ball is. So the last thing I did, I'm still trying to understand and process this, but I thought for a hackathon, why not show it? If you're familiar with, if you remember back in the day of Foursquare and check-in data, and you remember we all used to try and be the mayor of various locations, I thought, well, what if we look at the court as a check-in process and look at each point on the court and understand which player's checking in the most to each of the different spots on the court. And what these heat maps show is that data. So the gray is the opponent. The blue is their team, so on the left, Houston, on the right, Golden State, and then the red is the squares on the court where each of those different players are the mayors of the court. They consume that spot the most of any of the players on the game. And so those are interesting signatures. I'm not quite sure what to do with those yet, but I thought it would be fun to show. So that's it. So thank you very much.
Student division. Our first finalist in the student division is Bailey Mitchell from William & Mary.
Is this it? Okay. Hi everyone, I'm Bailey Mitchell, and like they said, I'm from William & Mary in the student division. And I know I wanted to, when I got this data, go through kind of my initial thoughts I'm going to tell you guys about, go through the challenges I faced on the day of the hackathon within those 6 hours, talk about the story I did decide to tell, and the methods I used, the findings I came up with, and kind of go through some further ways to use this data and kind of get more out of it. So initially, I know with a Warriors and a Rockets game, there's a lot of excitement, there's a lot of hype. So what can I do to add to that story? So I knew I was going to need to use all-stars. I was going to need to talk about clutch shots, because that's why everyone watches the NBA, and think about what plays are going to make a difference. So that's what led me to the late in the shot clock situations, because they're kind of mini end-of-game situations, and that's what everyone loves about the NBA. So I knew I wanted to analyze the matchups at the end of the shot clock relative to the all-stars. So Chris Paul, Steph Curry, James Harden, Kevin Durant, and then determine the effectiveness of the players offensively and defensively. Now, on the day of the hackathon, I got the games and realized that the limited games led to limited head-to-head matchups late in the shot clock. So I think Chris Paul and Steph Curry and them, I only got them like 3 times late in the shot clock as a matchup. And so I didn't want to kind of make some assumptions based on those just limited matchups. Also, not all the all-stars were playing in some of the games. So I wasn't able to get a lot of Kevin Durant and James Harden data just because they weren't playing in those games. And also thinking about how I wanted to define late in the shot clock. So you could look at something like 5 seconds, 8 seconds, 10 seconds. I ended up going with 10 seconds just because I feel like that's a natural fit, and also to kind of increase the scope. So again, focusing on the Warriors and the Rockets game specifically because I wanted to look at those matchups, and then using the tracking data to figure out when those leading scorers had the ball with under 10 seconds left. So here we can look at James Harden and Kevin Durant. And I kind of didn't get a whole lot out of this. So you see James Harden and Kevin Durant both have the ball pretty regularly late in the shot clock, and they have it both halves. However, when we look at Steph Curry, we can see that when the Warriors win, he's really active in both halves. So he's getting the ball late in the shot clock in both halves. However, when they lost, he really only got it 1 time in one half, and then maybe 1 or 2 times the other half before. So this tells us that Curry needs to be looking to have the ball late in the shot clock and looking to be really active for the entire game. However, when we look at a player like Eric Gordon, we see that when the Rockets lost, he was really active late in the shot clock. But when the Rockets won, he only had the ball, looks like, for 1 possession when he got to the rim late in the shot clock. So this tells us that players like Harden and Chris Paul need to look to have the ball in their hands late in the shot clock and not leave it to Eric Gordon to try to be effective. So kind of looking to further this, with more games, you're going to get more matchups, and you're going to be able to see more of what those head-to-heads look like as opposed to just the players as a whole. So that could lead you to understand more of what each matchup will yield. And then looking to increase the scope. So analyze all the players' positions, not just the ones with the ball. So you can look at what things look like as Steph Curry comes off of a ball screen, or how things play out when Kevin Durant has the ball at the top of the key. And then also looking to organize the possessions as types of offenses. So you can see the effectiveness of the ball screen late in the shot clock. You can see the effectiveness if Kevin Durant has the ball in the paint in an isolation situation late in the shot clock. And then use those statistical elements everyone's been talking about to decide whether things are effective or not. So the gravity, how players are moving as Steph Curry comes off of that ball screen, things like that. I think most importantly, one of the coolest things that could come from this is deciding if being effective late in the shot clock allows you to be effective late in the game. So it can almost become an R&D type of situation for a team where they're implementing things late in the shot clock to see how they will play out if they're needed late in the game, and seeing which players are actually going to end up being more clutch in the end of a game as opposed to just an end of a shot clock. So that's all I have for you guys. Thanks everyone for coming to listen, and I'll take any questions.
What selection bias do you think you're introducing by focusing on late in the shot clock?
Yeah, this is definitely a vacuum situation, because if you're the Warriors or the Rockets, you want the ball in your all-stars' hands late in the shot clock. But I think it allowed me to tell a specific story and definitely find out how those would play out in the rest of the game. So there's definitely some bias that's there, but once you're in that zone, I think it's really applicable and necessary for a team to look at. Anything else?
All right, our next student finalist is Benedict Brady from Harvard University.
Hi everybody, I'm Benedict Brady, and I wanted to suggest kind of a framework for evaluating favorable matchups in NBA, like head-to-head games like the Warriors and the Rockets. So the first step that I took here is I decided to cluster all of the players in the data set so that we can kind of combine them and increase our sample size. Like a big problem with this data set is that we only have about 10 games or so, and so we're not gleaning enough meaningful information about each player over the course of a longer season. So what algorithm did I take to classify these players? I basically was looking at where they spend time on the court, specifically in a half-court offense. So you can basically take the points in time where every player on both teams is essentially within about 30 points, or 30 feet of the basket, and you can assume that that's going to be a half-court play. From there, you can look and see you can divide up the court into 25 pieces and figure out how much time each player spends in a specific part of the court. And then we naturally see how many clusters that falls into in decay means. So there's not quite enough data here to conclusively say that there's more than 1 or 2 clusters, but we kind of see a local minimum or a local maximum of the gap statistic around k equals 9. And here are 4 example clusters. We can kind of see how the data separates a little bit. So we have the player that plays all over the place. We have the player who plays mostly just in the middle. We have the player who just hangs out in the corners of the three-point line. And then we have the player who really doesn't have an outside shot and is basically just hanging out around underneath the rim. If you're going to expand this research, this is a reasonable set of features to start with, but you obviously are going to need a lot more features to actually cluster players, where they're taking shots, where they're getting rebounds, all these sorts of different instances on the court will give you a much better feel for exactly what type of player this is. But just for a basic proof of concept of my clustering algorithm, I'm just going to throw up, this is like a pandas output, but whatever. These are specific, these are the 9 clusters that I came up with, and as we can see, you can see similar player types in the same clusters. You can kind of see this dividing up by player type and a little bit by handedness, which is something that you would expect. The next thing I wanted to do here is we're taking the specific Warriors-Rockets matchup, and we're interested in figuring out what player each person is matched up against for most of the game. Because through this, we can kind of glean some more information about what their matchup is like. So we're taking just the average proximity of each 2 players over the course of a half-court offense throughout the entire game or throughout the entire 2 games. And this grid shows us which players spend time near each other. So it kind of makes sense that Chris Paul and Steph Curry would spend a lot of time near each other, and that's something that is borne out by the data here. So the next step here is to figure out who is the closest defender on most plays for all of these players on the Rockets offense. And this is what we see, and these are the clusters that they fall into. And so the nice thing about the fact that we've already clustered the database is that we can figure out how they play against specific cluster types as opposed to figuring out how they play against one player in specific. And so we've labeled the clusters of the players that they play against, and then we can go on the next slide, we can take all of the players in the database and we can run like a very simple metric, but this is just their shooting percentage versus each cluster type throughout this 10-game data set because we have matchup data here. And so we can essentially see, okay, Clint Capella plays well against cluster type 0 and 1. So we want to drop plays where when he specifically versus someone in cluster type 0 or 1, we have him take the ball and take a shot. So what are the implications of this? Yeah, it's nice to figure out which matchups are good for players. Clustering allows us to increase our sample size. It also allows us to basically create a proximity metric for players, which is nice for just like common player type stuff. We can also implement this on defense. So if we see that a player in cluster type 3 is giving James Harden a lot of trouble, we can put him on James Harden during our defensive possession. And then we can figure out which players spend time near each other on the courts, which is just kind of another slightly valuable thing. But what are the drawbacks of this? Yeah, we need a better offensive metric. Like field goal percentage is something that I put together quickly because I wanted to like provide some sort of example here, but obviously that's not how you measure how good a player is playing on offense against a specific matchup. And we're not understanding any variance inside of the specific cluster. Something that people talk about a lot, but when you cluster players, you're essentially like reducing them to the mean of the cluster, which is losing a little bit of explanation. So maybe like constructing a secondary model, like some sort of hierarchical thing where you not only understand the cluster type, but then you understand how they exist within that specific cluster. Thank you. Any questions? One question.
Hi, I really enjoyed your clustering algorithm. It's really interesting use of sort of locations on the court. Specifically with the players that showed sort of tendencies to be all over the court, do you think you could use those for optimization of putting them against different matchups based on what's the biggest demand for your team?
Optimize it based on what, did you say?
So if you've got a cluster that can basically operate all over the court,
yeah.
Do you think that will mean that they can be plugged to fit any of those other clusters? If that makes sense.
Yeah, that's an interesting idea. I mean, once you've reduced something to a cluster like this, and you have like a spatial algorithm, you can kind of like add clusters together and see what it produces. So like that's a reasonable approach. You can also like look specifically, okay, when they're exhibiting character traits of this cluster, how are they playing versus exhibiting character traits of the other cluster. When you have data that's this granular, you can kind of dive a little bit deeper into that type of stuff. All right, thank you.
And our final finalist, Jason Feldman from Davidson.
All right, so I'm Jason Feldman from Davidson College, and I wanted to look at shooting analytics in terms of kind of where do guys tend to miss? Do they miss long, short, left, right? I know there's a paper sort of about that, but I think that might be not from in-game situations, so I was looking at kind of the in-game situations of that. So kind of a little background. People often with the optical tracking data tend to focus on the players, rightly so, but the ball's also in there, so it kind of gives the ability to look in terms of where do people miss on their shots and makes, things like that. And obviously there's shooting implications. If you know a guy is always missing long, then that's something you can work on in practice. You do have to be careful that shooting's psychological, so you don't want to mess with them too much, but it is information that some guys can take And then obviously in terms of rebounding, if a guy misses long, you know where those are going to go. If a guy misses left, right, it could definitely help players in terms of rebounding. So what I did is scrape play-by-play to match up with the tracking data to find out where the shots occurred and who they were taken by, and then match that up to the tracking data, and you can figure out with the ball where guys missed. Obviously, the data is a little bit messy, so it's not perfect, but it definitely gives a pretty good sense. So I looked at the head-to-head matchups between the Warriors and the Rockets that were included within the data, and then created kind of in baseball you have spray charts, so kind of like that. So here's one example looking at 2-pointers versus 3-pointers. What you kind of can see is 2-pointers, you tend to have some more left-right misses, whereas 3-pointers, you tend to have more of the long-short misses, which is interesting. In terms of players I wanted to look at, obviously, people tend to look at Curry, Durant, Harden, but I wanted to look at the real shooters, Nick Young and Gerald Green. So obviously, it seemed like both of them had pretty good days. Obviously, usually there'd be a few more blues. Those are the misses, but you can see Nick Young tends to miss left, whereas Gerald Green tends to miss longs, which is definitely something to keep in mind in terms of rebounding. I also looked quarter by quarter where players tend to miss. You see first and second quarter, it looks like it's pretty spread out, whereas in the third quarter, you tend to have more of these both short and long misses. Then once you get to the fourth quarter, there's almost no misses long. You just tend to have a lot of guys missing short. So I think that's something really interesting. So in terms of areas that I didn't get the chance to explore that I think could be really interesting off of this, obviously certain players tend to miss in certain spots, and given the scope of the data we had, I didn't want to dig deeper, but if we could look at, say, oh, what about this player on this type of shot? If you know Steph Curry on floaters tends to miss those short, whereas when he's taking a step-back three, his miss is long. That's definitely information that as a rebounder would be great to know, and also something you could possibly address in practice. Also, in terms of looking at how many minutes a player's played versus where he tends to miss, if you say after 30 minutes that this guy tends to be this much short on his shots, that can be helpful for a coach to know so that they can make decisions with that. And I think it also could definitely be used as a scouting tool. I know sport review, or I guess the tracking data is starting to become more of a thing in college and will only happen more in the future. So if there's somewhere that, obviously I didn't have the data to explore on it, but say a guy who misses short, long, can have his shooting fixed more than someone who misses left, right. So say we look at a guy like Jason Tatum, who obviously didn't shoot as well in college as he has in the pros. Maybe there's something with his misses tend to be something that's more correctable versus another player who struggles with a longer shot in the NBA. I just think it would be an interesting area to explore in the future. So thank you for your time, and I'll take any questions.
How did you determine where the misses were? Was that in the data set you guys were given?
Yeah, so you have the XYZ of the ball, so you can, if you know when the shot happens, the times are stamped, you can figure out kind of where the ball kind of made contact with the rim or went in.
Did you consider, as far as missing short, left or right, did you consider where they were shooting from?
That's something that obviously I didn't get to do given the time frame, but obviously in terms of the future, you know where they shoot from, so you can kind of just orient it based on that, but that was not something I got to do for this.
The paper yesterday only looked at stationary shooting. Did you do the same, or did you take velocity into consideration at all, like side-to-side movement while the shot was happening?
So this is just from in-game, so players, whatever it was that the shot they took, that's what they took. So I think this is something, obviously just shooting stationary, and even if you are shooting on the move in practice, that's totally different than a game situation when you have defenders. And kind of you can look at that, say, how close was the nearest defender? If there's a close defender, do you tend to miss long? That's another thing you can kind of explore.
finalists, on behalf of ESPN, I'd like to thank our co-sponsor Ticketmaster, and I'd like to thank our judges for the competition, Corey Jez from the Utah Jazz, Ben Falk from Clean the Glass, and John Carnahan from Ticketmaster. We are going to have the grand unveiling of the winners of the hackathon during the Alpha Awards this afternoon, so come by, check it out, see who actually wins it all. But congratulations to all of our finalists and our participants. Great job.